안녕하세요. 최성훈입니다. 조셉 초이라고 하는데 제가 이제 로체스터 대학교의 광학 인스티튜트에서 존 하월 교수님, 저의 교수님 이제 물리과신데 제가 거기서 왔습니다. 오늘 투명화의 방법에 대해서 제가 말씀을 드리겠는데 저희가 이제 로체스터 망토라고 불린 그 한 예를 제가 또 시연도 하고 그거에 대해서 좀 더 집중적으로 설명도 하겠습니다. 일단 아직 제 프레젠테이션이 안 떴는데 제 소개부터 하겠습니다. 저는 이제 미국에서 하와이에서 태어났고요. 유타주 미국 서부 쪽에서 자랐습니다. 근데 제가 중3에서 초등학교 3학년에서 중3까지 제가 한국에서 청주에서 학교를 다녀서 이제 한국말 좀 하게 됐고 저희 부모님도 저희 가족이 이제 한국 분이시라서 제가 사진을 좀 보여드리겠습니다. 잘 안 넘겨지는데요. 사진을 좀 있으면 이제 나올 건데 저는 이제 결혼해서 이제 애들 둘도 있고 이번엔 남자아이가 돌도 맞이해가지고 돌잔치도 좀 했습니다. 그리고 학교는 저는 이제 유타주에 있는 브리감영 대학교에서 학부를 졸업했고 석사는 코넬에서 물리과하고 지금은 이제 박사 과정을 잠시 좀 회사도 다니고 뭐 사업도 좀 하면서 쉬었다가 이번에 다시 박사 과정을 시작해서 이제 양자광학 쪽에 제가 박사 과정 학생으로 또 연구를 하고 있습니다. 예, 저희 가족이고요. 지금 결혼해서 이제 애들 둘 있고 저희 지도 교수님 존 하월 교수님이십니다. 이제부터는 이제 영어로 제가 말씀을 드리겠습니다. 왜냐하면 제가 이제 미국에서 공부를 했으니까 전문 용어는 한국말을 잘 모르고 또 아마 가장 중요한 이유는 제가 영어로 말씀을 드리면 더 멋있다고 사람들이 얘기를 해서 제가 영어로 바꾸겠습니다. Okay, so now I'm going to speak in English the rest of my presentation. First, I will give an outline of the talk that I will give. So, to understand where we are with cloaking, just want to give you a historical background in invisibility cloaking, and that will probably help you appreciate what the Rochester cloak actually did in the field. And then I will talk about scientific cloaking, which really started heavily in 2006 in a field called transformation optics. Now we'll talk about ray optics cloaking and how a one-directional ray optics cloaking changes some of the deficiencies in some of the transformation optics cloaking. Now we'll focus on ray optics cloaking in the multi-directional, so different directions, and that is where the Rochester cloak comes to be. Okay, so in history and in fiction, the Greek mythology, there's a cap of invisibility. Athena, Hermes, and Perseus used it. And then there's a cloak of invisibility in fiction. For example, King Arthur, Jack the Giant Killer, Star Trek, Harry Potter, and then, of course, the ring for the Lord of the Rings. Most people know the invisibility cloak for Harry Potter, and that's where a lot of the media attention was placed. But you can see as Harry Potter wears this invisibility cloak, he disappears. And then there's also an option for chemicals to make someone invisible, and that was the basis for The Invisible Man by H.G. Wells. So there's also invisibility in magic shows. For example, David Copperfield famously made the Statue of Liberty here disappear. And then there's also an example in the Science Museum in Israel. where the body disappears by a clever use of mirrors or optics. So you just see the head here and it appears as if the body is gone. You can explore more of that in a YouTube video. So now let's talk about invisibility in science. Well, in order to do that, I'm going to first talk about cloak and what that means in this talk, because I think that causes some confusion in not only in Korea but also in the US. Most people, when they think about cloak, they think about something that you wear. In Korean, it's mangto, and that's what has been translated from Rochester cloak. They translated it as mangto, 로체스터 mangto. But what we used in terms of cloaking was to hide, or 숨기다. That was the original intention for cloak. And in English, there are two meanings, these two meanings. But a lot of people tend to think when we say cloak, it's something that they wear. But that's not necessarily what we're going to talk about. Of course, you can wear lenses, but it will be uncomfortable. So that's the angle that we've taken, is we are just going to be talking about how to hide something, how to make something invisible. And that's what we'll be using in this talk. Here's a demonstration of that with our Rochester cloak, of my eye being hidden or being made transparent. There are some active camera cloaks. What they do is they use a projector to project an image of a camera behind the person. So there's a group in Japan that demonstrated this. Very interesting, I think. Here's an example. So the person is wearing something, and there's a camera behind that person that is connected to a computer that projects the image onto his wearable material. But this only works really from the front. People in the back recognize that there's someone there. So it doesn't really work perfectly, but it was a very interesting demonstration. A Mercedes-Benz commercial also utilized LEDs, I believe, or LCDs. What they had is they had cameras on the back side of the car, and then that would project that image onto the display panels up front. And so it appears as if the car is gone, just from the front, of course, but not from the back. So transformation optics was a new beginning for scientific cloaking, and it started in 2006. So I will talk about this because it's quite significant if you are in the field of cloaking and what science has done with that. So transformation optics, that's what it's called. What they do is they create a virtual space with a hole or a region where light does not enter. And if light does not enter that region, that means that region is hidden. No one can see it. So in this case, the red circle is where no light can go. And so this is just on paper. In theory, we have this virtual space. Then what you do is you map that to a different coordinate using math. It's a very beautiful theory. And then what you do is you map it to a physical space. So here, the physical space is shown here, and you can see there's a blue shaded region here. That is where you build materials to be able to bend the light around a sphere. And when you bend the light around the sphere, then you have light not entering that sphere, so that sphere becomes a hidden region. It's where you can put something and no one will be able to see that. And that is done by the blue shaded materials that use metamaterials, and that means it's artificial materials. You do not find this in nature. You artificially make it using the theory of transformation optics, where you did a coordinate transformation. So it's actually a very beautiful theory. They suggested this in 2006, two groups in 2006 in Science, very famous journal, but they were back to back. The next page was another group that presented this. So those were the two groups. One is Leonard from England, he proposed the top two-dimensional transformation. And then there's another group in Duke University in the USA, Pendry, Schurig, and Smith, and they proposed a three-dimensional transformation, which is shown at the bottom with the sphere. They demonstrated this in 2006 using metamaterials, and it was a two-dimensional microwave cloak. So I'll explain that a little more, but this was the first demonstration using metamaterials to actually cloak an object. So you can see here, there's a pattern of materials that's in a circle, but it's only flat, and that's why it's only two-dimension. If you look up or down, you can see the cloaking region. But if you're in the same plane, then you will not be able to see through it as long as you don't move up and down. But the other issue is it uses metamaterials, and metamaterials are very difficult to make for the visible spectrum. And so they did this first demonstration using microwave cloaks. So it's a different frequency. And they demonstrated this with simulations and experiments where you see light field moving through the circle, and it sort of bends around and then comes back together. And the one on the left is, I believe, simulation, and the one on the right is the experimental realization of that. And you see they sort of match. So it was a great demonstration, and a lot of people were very excited about this result. Okay, so transformation optics, it was very revolutionary in terms of not just cloaking, but material design and using that to apply to something that might be useful. Omnidirectional, that just means it works for all directions. So within that two-dimension, you can go from here all the way around, and it will still cloak that center region. That's very powerful. However, it becomes difficult because they're doing full field as well, and that means you're using the full nature of light and cloaking it for the phase and the amplitude. I'll talk about this more later, but here are some examples that aren't necessarily transformation optics, but inspired by transformation optics. There's a time cloak where they separate out temporal light using a time lens, and then they cloak an event in the center, and that was a time cloak. That was published in Nature. There's another example of a thin shell radio wave cloak, and that was also inspired by transformation optics. In fact, that was sort of a transformation optics cloak. And then there's also seismic cloaking, where people built materials that work for earthquakes. So very interesting, earthquake cloaking. So there are some difficulties with transformation optics. Metamaterials, you're using artificial materials to design in a spatial pattern. So I'm showing you some lenses that use metamaterials just to demonstrate that you need to pattern these. But these aren't really used for cloaking. It's just to demonstrate that you need to specifically pattern these materials, and that's very difficult to do. The other thing that's difficult is to make it work for the visible spectrum, the colors that we all see. It's very difficult because the wavelength of the colors that we see is very small, and you need these metamaterials to be even smaller than that by 10 to 100 times smaller. And that is very difficult because at that point you are starting to use a few atoms to build a structure, and then you need to lay that out to make a large cloaking device. That's technologically very difficult to do, though that is sort of possible to do. The more fundamental limitation is that it only works, when it does work, it only works for a narrow band spectrum, meaning it only works for a small range of frequencies. Usually people do it for a microwave region, but even then it only works for maybe a few frequencies or very nearly those ideal frequencies, and that's a problem. The other thing that's a problem is anisotropic material. That just means you have to change the material pattern and the properties depending on which direction you're going, and that's a difficult thing as well. The other thing is you have singularities, meaning you have like infinite velocity, or you have negative index of refraction, which is not found in nature normally. The main point here is that it's difficult to make for the visible spectrum. So people then said, okay, well, can we do something with ray optics instead of transformation optics to do cloaking? Yes, and let me talk about the difference between full field optics, which is transformation optics, and ray optics. Full field, if you have taken a science class, you know that light is a wave, an electromagnetic wave. That is the full nature of light. That's what full field optics does. It considers the whole wave. And you can see that the wave moves up and down, and it moves in a certain direction. Ray optics cloaking, what they do is they just look at the direction and the power. How much light is going in this direction? That's it. It doesn't consider the wave nature. So it's easier to do. And because it's easier to do, it makes things a lot easier to actually build for cloaking. And here's a picture of in using ray optics where you have lenses focusing or diverging. That's using ray optics because you're only considering the power and the direction of light. You're only considering the direction of the wave, and you draw it as an arrow. So ray optics cloaking. It allows you to do macroscopic cloaking and visible light cloaking, meaning it can do large objects, and it works for the colors that we see. It's so far the first unidirectional or ray optics cloaks were for unidirection, meaning for one direction only, or discretely multi-directional, meaning it only works for one direction, or you have to go maybe 30 degrees and it works for that direction, and you go another 30 degrees. So you can see here there are 6 angles. It can go straight left to right or right to left, or maybe 30 degrees or 60 degrees from there, but you can't do anything in between. Here they cloaked a fish, and then our group, we used water in a tank to cloak some toys. So here, this is just glass. We haven't filled it with water. You see 2 toys, and then when we fill it with water, you see the red toy behind through the toy in the middle. But again, this only works for one direction. If you use it for other directions and you look at it from different directions, what happens is either the background will shift drastically or you will be able to see the hidden object. In the case on the left, the background is so close that when they did test it, it didn't change a lot. But when you put the background far enough, you will notice the change, and that's what the Rochester cloak would demonstrate. So the first version of our University of Rochester ray optics cloak, here's an example using mirrors. My advisor and his sons did this about a year ago. And this was, the setup is you have 2 90-degree mirrors and another 2 here, and it just reflects light. Light goes in, bounces, and then comes out. The problem with that is the magnification changes, so the size changes. And you can see that here. The trash can behind on the left side is different than what you see through the mirrors on the right side because of the magnification change. Here's a demonstration. The first video will be shown. 첫 번째 영상 좀 부탁합니다. Okay, so this was actually a YouTube video. Got a lot of hits. I just want to emphasize that unidirectional ray optics cloaking is actually very simple, or it can be very simple. You can just take a picture with your camera, put it on a computer, and you see that this is courtesy of my advisor. His arm or some of his body is cloaked, but it only works for one direction. Now, let's talk about multi-directional, continuously multi-directional cloaking, because that's where some of the formalism comes into play. Limitations of previous cloaks. The previous cloaks, so far that we know, they haven't been 3D transmitting continuously multi-directional cloaking. And so this is the first that we know of for visible light. Usually it's very difficult to combine all of these, making it broadband, meaning it works for a lot of different frequencies or wavelengths. making it work for optical visible frequencies, making it isotropic. It's just easier to make. If you do that, you can use standard optical material. And the other thing is to make it scalable and large is difficult. Full field matching, so for the full wave nature, combining all of that is very difficult to do. We haven't combined all of that, but we have combined most of that. And we have solved that for a small range of directions. So here's the second version, and I just want to give you an idea of how this was developed, because people ask this, but I think it's important because you can see how maybe perhaps innovation comes into play, and that might be able to help me and others be able to be more creative down the road. So the goal was to make a continuously multi-directional cloaking. So it works for when you change positions and you look at it, it still works. Here was the first idea from my advisor. So you have a lens, you have mirrors, and bounces off a mirror, comes off another mirror, and then it goes off through a lens. That was his first idea. And he told me, Joe, why don't you try to simulate that? So I did, and it seemed to work. I did some computer software simulations with rays. Here, let me just show you. There are 3 different angles. So you see different colors, red, green, and blue. Those represent different angles. And that's what I mean by multi-directional. It works for these different angles, but when I say continuously multi-directional, it means it works for any of the angles in between. And that's what continuously multi-directional does. And so this seemed to work. However, I tried to improve this because I wanted to make it better. I wanted to be able to pull some of the mirrors up and make this work for larger angles. Now, if you want to make something work, you first need to be able to define things quantitatively. So let's first talk about what it means to be a cloaking device, how to cloak something. Well, here's an example of Halo. It's not a perfect cloak, but this gives you the idea. What does it mean to be a perfect cloaking device? That's a good question to ask, and that's the first question that I asked. Well, it means the object becomes invisible. So here, Halo, the soldier, will be invisible. And that's the same thing as making it actually transparent. That's what cloaking does. So how do you quantify that? Well, there are 2 requirements. One is you want both the hidden object, in this case, the Master Sergeant soldier, and what he's wearing to be invisible. And that is the same thing as making all of that empty space. That's the key point. You want the device and the object that's hidden to act as if it's empty space. Because if I place an empty space in front of you, you cannot tell that it's there. The other thing is you also want a non-zero volume to hide an object. That's the second condition. You need to have something that is hidden, or else it's just pointless, I suppose, and it's not cloaking. So what does it mean to be a cloaking device for light rays? Well, you can say, okay, what's the first thing that we could do? Don't do anything and just replicate the rays. So from the left, you see the arrows, the rays of light, and then on the right side of the box, you'll see the same thing replicated. But what does that do? Well, it makes it so that the object and the image are placed at different places, and that's not what we want, because the object is not the same as the image. What we want is we actually do not want to touch the rays at all. So the rays should just go straight through as if it's going through empty space. That's the key point. You want your optical system to replicate empty space. And in this case, you can see that if that happens, then the object is the same as the image, and you don't know it's there. So we applied this to our ray optics cloaking version 2, and we use what's called ABCD matrices. Very simple, actually. It works for small angles. That's why we call it paraxial ray optics. That means just that the angles U and U prime here are small. And that just means that we replace the lenses and the mirrors with 4 numbers, ABCD matrix. And that's how it is. It's very simple. That's the simplest theory that you come up with in terms of optics. So we said, okay, what does it mean to be a perfect cloak? That means the system is empty space of the same length. So that means if you have a system that's L in terms of length, you want that to be the same thing as empty space of the same length L. And there is an ABCD matrix for empty space of the same length L. and that's just 1L01. That's it. That's all we do. You solve for this, you have an ABCD for a cloak. And that replicates empty space. That's the main idea. So this is the heart of our theory. Very simple. 4 numbers that you match. So we fit it to this, and it actually does work. I was surprised that you can have lenses and mirrors, and it still replicates empty space. However, when I actually built it, it only worked for 2 dimensions. If you want it to work for 3 dimensions, you have to build it. You have to rotate things, and it's a lot harder to make. So we said, can we simplify this? Well, let's go back and see if we can build just a cloak with just lenses, and that's what we did. So we tried 1, 2, 3, and 4, and 1, 2, and 3 will not allow you to cloak. What happens is, if you want it to act as if it's empty space, meaning it fits the ABCD matrix, the 4 numbers, and you want space so that an object can be hidden, you need at least 4 lenses set apart correctly. And this replicates a system with empty space of the same length, and it provides a non-zero volume to hide an object. So here are the results. Background image matches, so as you see, I'm changing the camera angle, position, and the grids in the background move. But the grids through the lenses also move and match it. That's what it means to act as if it's empty space. And then we have a region where you can hide something. So with the 4 lenses, this works for a range of directions, and that's the important thing. So here, if you notice on the figure E, that's what's going on. Is light ray is focusing, diverging, focusing, diverging, focusing, diverging. Where the lights do not pass, that's where I put my fingers. And if the lights do not touch my fingers, that means you cannot see it. I only see you because light hits you and comes to me. If light does not hit you and it comes to me, I do not see you. And that's where I put my fingers. So this is the simplest design. That's why you need to let light pass through the center. We do have other designs that let you hide a complete object, including the center, but it's a little more complicated. Okay, and this was just published in Optics Express officially yesterday, I believe. So here, this is the second video. So as you can see, my fingers are still cloaked. You don't see my fingers. And you see the background grid matching what you see through the lenses, even when you're moving, even when you're changing angles. That's the key point. Making it work for one direction is actually easy, but to make it work for a range of directions, that's a little more difficult. It's not too much difficult, but it's doable. So here you see, I put my fingers in between the first and second lenses where it's focused tightly. That's where I get the larger cloaking region. So now I will do a demonstration. Okay, so here's the original Rochester cloak that I have shown. Here's another version. What we did here is we made the lenses larger and tighter using special lenses, but we sacrifice the image quality, but we get a larger cloaking region for larger angles. Here, the image quality is very good, but it's smaller ranges of angle. So I'll put my finger here. Okay, and as you notice, if I pass through, you can see my fingers. That's why I need light to not pass. And that is the cloaking effect. And here, you still cloak, but it's not as good. It's not as tight. And even here, same thing. You can cloak. So as long as my fingers pass where light does not go through, then you do not see it. And then if we can change the direction of the camera. So as the camera moves, you notice the background changes and matches. The lines line up. 반대쪽으로도 할 수 있을까요? Yeah. Okay. Great. So you see my fingers were still cloaked even though you were changing directions. Okay, so possible applications. Some ideas, I've just mentioned a few ideas. You can hide a satellite perhaps, or make the truck behind you disappear and see through, so you can see through it. Or many different applications in terms of maybe for artistic purposes, or hiding a building, or making a wall become a window instead. But I really think that the practical uses will likely come from the public, designers, inventors, entrepreneurs, the industry, artists, engineers, and I think they are the ones that will use our formalism, because it's not just limited to 4 lenses. We've just laid down the basics for it, that they will be able to use that to actually come up with hopefully useful products, and we just provided some suggestions. So I would just like to first acknowledge, or lastly acknowledge, my advisor, Professor John Howell, and then a few of my colleagues that helped me, Aaron Bauer, Robert Gray, Kyle Firschbach, Greg Howland, and of course the University of Rochester Communications Office, who provided the many different videos and the photos that were quite amazing. David, Leonore, Adam, Matt, and Larry, and then my funding agencies, DARPA and the Army, as well as I would like to thank TechPlus for inviting me. It's been an honor and a pleasure to come to Korea and present to Koreans here. 우리나라 분들에게 이걸 나눌 수 있어서 정말 영광스러운 걸로 알고 있습니다. 감사합니다.